Welcome at this presentation on PLCopen Motion Control, where I will show you how and why we did motion control. Hello, my name is Eelco and I'm the Managing Director of the organization called PLCopen, and I will guide you through this presentation. First, let us go a little bit back in history. Not so long ago, there were well over 100 motion control dialects. And that means there were not many commonalities between them. And everybody spoke a different language. So it was very difficult to learn, generically understand each other. Even logic was a complete different language. So it was very difficult to communicate, to integrate those. If you look to a classical mechanical design, there was only one motor, and the rest of the functionalities were coupled there via mechanical links, via gears, via belts, via all kinds of constructions there. And that came with a lot of problems. Yeah? You had too many parts, it was expensive to build, you had a high level of maintenance, you needed oil that could be encapsulated in your packaged products, so it could contaminate that one. Overall, you also had more waste in these lines, so we had to find new ways. And the new ways were there to go from this mechanical solution to what we call a mechatronic solutions. The combination of mechanics, electronics, and even on top of that one, software. So that means that if you look to these belts and these chains, and you had a certain timing problem like you have in your engine in your car, then you know that this is not the right way. We want to move these functionalities to a software solution, to software commands. And that means if we take the same mechanical design, which was a packaging machine, and we look to all the functionalities that are there and very closely put a servo technology there, then you see that we have a complete different design. So we take out the pulleys, the belts, the drive sprockets, the spline shafts. We take most of the gearboxes out, but of course we add motors. The big motor is gone and we replace them with smaller motors local to the functionality where they are needed. And overall, as you see, that leads already to 81% of reduction of components. So that's a good starting point. And in praxis, the packaging machine was converted with these concepts from something like this, which needed oil and a lot of maintenance, to something like this, where if you open up the bottom part, there is no master access there. There are no mechanical links there. So it's much easier to work with. Overall, we call this faster, better, cheaper. Something that all the industries need. It's not just industrial automation. So PLCopen is supporting this transition because we see, of course, the controller needs software. And the software needs reusability via abstraction. I'll show you what I mean with that one. Software needs standards, and that's where the role of PLCopen got in. So first, something on this abstraction. Here you see a function block. It has a name, inputs on the left side, output on the right side, and this is the graphical representation. We can do a textual representation too, but it's easier to show. Internally, the hardware view, this function block contains code, and the code will use the interface, perhaps the network, to connect to an intelligent drive, to a motor and to an encoder and get this up and running. Yeah? It can be that it's a network, it can be that it's built with modulation, with a direct connection to the power stages of the drive. But from a software point of view, as you see on the left, it's the same look and feel. That's what we call encapsulation information hiding. That's what we call abstraction. You do not see the details on that level. I can start moving the motor and I do not have the details about how that is connected. So here you see a real function block, move absolute. On the left side you see again the inputs. On the right side you see the outputs. They're all linked to the data types. So you see a link to the axis, and then you see the execute, and then you see some profile information, position, where do we want to go, the move absolute position we want to move the axis to, and then a certain profile, velocity, acceleration, deceleration, and jerk. And on the outside you see when it is done or when it is busy, and if it's done correctly with error ID. Now on the top you see that the axis ref, the reference to the axis, is a little bit different than just an input and an output. It goes right through. That's what we call in-out variable. It's both an input and an output. And the nice thing of that one is that the reference is outside of the function block. So we really reference to a structure that is outside of the function block. What you see in practice is that you have this function block, and there the axis ref, the structure is outside, so the real reference to the axis. And that's via some kind of conversion to this interface, to this drive, to the motor. The encoder information gets back. And that's what you want on a, well, every milliseconds, every 500 microseconds, or whatever time. Or even you can do it event driven if you want. Now the nice thing is, if I have a second function block that operates on the same axis, it operates on the same axis ref structure. Yeah, and that means that I can link these function blocks, and if the first one is done, the second one I can start with the execute. So this is very easy. And yeah, you see the abstraction. I do not know the details about the basics, about the network, about the motor, but still I can make that operational. Every function block has its same error handling procedure, error ID. The error tells you if there's an error, and the error ID tells you a number, a word, a number, which is related to the information there. Yeah? Why do we do a number? Because with a table you can easily convert a number to a string or to something that makes useful to you. And even in the different languages. That's not only English, it can be Japanese, Chinese, or whatever language you choose. And converting a number via a table is much easier from a language perspective. So on this basic idea, PLCopen developed a whole suite of specifications. Yeah? Part 1 is the basics, the function block for motion control. That's where the whole concept is in now. Part 2 is the defined extensions. This is more historically. It's now integrated in part 1. So part 1 and 2 are merged. Part 3 deals with user guidelines. And that helps you to understand how you can use this. Part 4 is coordinated motion. Think robotics. I will show you later what we mean with that one and what we have done there. Part 5 are the homing procedures. How do I home my whole machine? Also there, I will show later what is in there. Part 6 is fluid power, some extensions for fluid power dedicated to there. And I will show you that set too. What is important that overall this is supported by around 30 companies and around 67 products. Now, of course, this is, there are more companies coming in. This is added on the table. Yeah? So check the website, plcopen.org, for an up-to-date list. But the importance is that you got a huge richdom of choice. 30 companies delivering all kinds of products there that helps you to fulfill your needs. Look into details, part 1, basics. It contains 2 sets of function blocks. One is the administrative set and one is a motion related set. So administrative is things like power, read parameter, write parameter, for single axis, for multiple axis, and the motion you go the move absolute, the function block that you saw, but you also can do a move velocity or a home, and you see we can combine axis in a camming or a gear in, gear out functionality. Part 2 extensions, that's now integrated in part 1, but it has the same structure, single axis and multiple axis. Touch probe, read digital input, set position, set override, torque related thing, and multiple axis, gear in pos, gear in position. So gear in at a certain position. Part 4, coordinated motion. You have the administrative again, and you have coordinated and synchronized motion. On the left, with the coordinated administrative function blocks, you build a group of axes, you add axes there, you link that to a kinematic transformation, and with that one, you start moving with the coordinated motion. Yeah? So this can be a complete robot. And then you start moving, and the synchronization is that you synchronize the robot to something else, or something else to the robot, a single axis. I will show you some examples. Part 6, the extension for fluid power, adds some specifics for the fluid power. And that means those are more warning related function block. Think if you have a hydraulic shovel and you're on a curved area of land and you try to switch to move it around very quickly with the arm, you probably can fall over. So you limit, the control can limit the velocity of those, the maximum velocity, make sure that you are safe within your shovel. Part 5, homing procedures is a little bit different. That's why I put it a little bit different in this row. This is specifically for the homing of your machine, the homing of your axis, if needed. So there are on the left homing procedures. And how do you do that? You follow a switch and you go over that one, or you do it direct, or you know it already because you have absolute encoders on the bottom. And on the right you see the related function blocks to it. And in order to finalize the home, if you're on the wrong side of the switch, the limit switch, you have to go back. So you got to do something there. And the last section, the third on the bottom, is homing on the fly, where you correct your homing on the fly while moving because you see a reference point. And that reference point, think about an AGV where your tires can be a little bit less when you have weight on it. So it can be that you measure it a little bit differently. Now if you have reference points, it's very easy to correct your homing position. You know again where you are. Part 3 are the user guidelines, and that shows you examples on how to use this. It shows you examples how to create your own user-derived function blocks. It's a basis to create your own function block libraries containing higher functionality function blocks. I'll show you one of those. That's the winding that I mentioned here. And it gives you examples in function block diagram, a ladder diagram, and structured text. And it's around 94 pages. So it's really content, what I would like to say. But it's not a training guide. If you use a specific environment, the supplier will give you the right training material. So here's an example where we use multiple function blocks on the same axis. So you see the axis going through function block 1, function block 2, function block 3, 3 times a move velocity. And you see at k, function block 1 has an input k with velocity 10. So if we set k, the velocity will go to 10. And if that's in velocity and L is done, we execute the next function block with velocity 20. And when that's done and M occurs, then function block 3 brings velocity to 0. This is the same example in function block diagram, but you see the same K, L, M that trigger the velocity 10, 20, 0. I even can do this in sequential function chart, where I have the several steps, and I go in the first one. You see that 10, velocity 10, and then velocity 20, and near the bottom you see velocity 0. So that's what we move. We do have one instance of the function block move velocity, and we feed it different values. Also specified is the combination of axes in part 1. So this is a Gearin. You see a master axis and a slave axis, and you want a certain ratio between the master and slave. And when the execute is done, you want to fix that ratio, and then you see on the other side when it's in gear, when this is done. And of course the error and the error are there. If I look to 2 of these function blocks, I connect them to my master, I connect them to my slave, and I do a ratio 1 in the first function block, and I do a ratio 2 in the second function block, with a certain maximum acceleration and deceleration. Then when I execute the first function block, it will move to a ratio 1 between the master and the slave, and it will set in gear when that is reached. And if I execute then on the same axis, of course, the second function block, it will switch over to a ratio 2 with a certain acceleration profile. So what you do is, that's what you see here in your timing diagram on the left. Execute first, the first in gear. It takes some time before the ratio is reached, and you see on the bottom the slave velocity increases from 0 to what the master is. And then with the second execute, it increases its velocity compared to the master with a ratio of 2. So you switch gears. but just in software and not on the way that we do it manually in a manual gearbox. A startup procedure, that's if I have connected just a motor and a drive and encoder, and I want to see if I've done that correctly, and so I want to create a small program that starts moving my axis. This is what you do. You do a power on, you do a home, and you do a move absolute. And then you know it's moving in the right direction, and if you've done that correctly, some of those. And this is independent of the architecture. So it's not very complex in that sense. And this is the information hiding that I showed you, the encapsulation of the functionality, helps you tremendously here to get your startup procedure and to check if you did wire it all correctly. Part 4, coordinated motion. I told you I will show you a little bit more on that one. So here it is. You see here in the middle PLCopen part 1 and 2, which are single axis related. And you have some of those combinations with the camming and the Gearin. But on the left side, you see what we do with part 4. We do coordinated motion. So we build a group of axes and couple that to the different coordinated systems. And with that, we can start moving. And then we have these synchronized motion items, where we say we have this group of axes and we want to link that a relationship to a single axis. So I can do an axis to the group or a group to the axis. And we got 2 other functionalities there. Track configure belt. So that's a configure belt that's running. And on top of that one, I want to make sure that my robot arm, or what's there, follows that one. And the rotary table. I'll show you some examples there. If I want to put glue on a window, which will be stuck to your car, I synchronize a single axis, the one with the tube of the glue, to the axis group, and that's the end effector in this case, what's important of the robot. I can do it the other way around. I got a press, and when the press is moving, I want to know where it is in its face, because then I know when it's open and it's safe to put a plate in or a plate out in this press. So the press can go on and on and on, and the robots just go in and out because they know where they are and how to synchronize to them. And tracking, now here I got the conveyor belt on the bottom. And imagine that there's a cake on it and I want to write your name on it, with some cream. And then, so I want to synchronize to the movement of the cake versus the name that would be written on it. So then I do a tracking to the belt. I showed you encapsulation. I will go to a next level there and show you even more how you can use it to create your own function block libraries. And for that one, I will show you the winding, unwinding. So I got a large roll of paper and I either wind it up in making it or unwind it if I want to use it by wrapping any product there, packaging. Think about a chocolate bar. So in order to have a good control, a good force on the rolling process, or the winding or the unwinding process, there are several ways of doing that. We call that in principle dancer control, that you have a consistent torque on your paper in that sense. And when I've decided how my dancer control looks, it's relatively easy to create a winding function blocks with a constant surface velocity. Yeah, I got my axis ref. I got only one axis, that's the one that's turning it in. And I got a spool radius, a minimum radius, maximum radius, and some profile there, and the velocity that I want to do that. Internally, if I double click on that function block, it would open. I can see some code in it. And this is the code. I do a move velocity and a stop, and the velocity is related to the radius because I want a constant surface velocity. So the amount of paper that I with every cycle, with every turn of it, if it's nearly empty or nearly full, it's still the same. So that's where the relation is, and that's where a certain calculation is done, the divisions, and make sure that I get the right values out of there. So I encapsulate this and create the function block out of it that I had there. And with that one, I go from the basic function block as defined. Here's on the bottom your PLCopen Motion Control function block, but also the logic and the safety and the communication. And I create function blocks which suits my application area. So I create my own library of function blocks with a higher level of functionalities, much closer to the problems that you want to solve in practice. And there can be several layers on that one. And for packaging, you can go to a level where you see these cutting, sealing, filling, capping, higher level functionalities that match the application areas that you want to fulfill there. And your application program in that case gets very small, very tiny, because it calls just the function block instances that are under there, and it gives us the right parameters. And the functionality is running there, so that's not part of your application program. That's part of your function block libraries. And we always advise to put a state machine on top of this hierarchy. And in this case, the example is an OMAC PACML state machine. And it gives you a consistent look and feel of your machines or your devices or of your production line at what level you are in this case. So PLCopen Motion Control provides a suite of specification that results in a suite of implementation, 30 companies, 67 products, a suite of suppliers, a fast-growing suite of users, and I hope we will grow there still. And that means we hope we give you a suite of advantages in that sense. Now, motion control is not the only part that PLCopen does. What PLCopen basically does is we combine the logic, motion and safety into one environment, giving you structuring, decomposition, reuse, and in the end less training. Think about 100 dialects, there's only one now left, and that's easier for your training. Even if you use different systems, the look and feel is consistently across those. On top of that, we add communication via OpenCOA, XML for exchange of programs, of projects, and of course training where we set guidance on how to improve the quality of your software development process. And that's our tagline, efficiency and automation, because that's what we want to achieve you. And I hope you have seen this, that using PLCopen Motion Control can help you to gain more efficiency in your application software development, but also in your maintenance and your installation. But for this, we need your help too. We as an organization are depending on our members, and we hope you will go there too. So for more information, please go to the website plcopen.org, download the specifications of motion control, and if you want to get in touch with me, this is my email address. Thank you for watching. There are more videos now available already. There are more to come. So keep in touch with us that we can inform you there. Thanks for watching.